In this video, we're going to talk about hypothesis test on two population parameters. So, one of the most useful applications of statistics, not just in business but in a lot of things, involves comparing two samples to examine whether there's a difference between whether the difference between these two samples is significant or it's just likely due to chance. And this lends itself quite well to the analysis of data from experiments. For example, a local YMCA in the early stages of telephone solicitation to raise funds for expanding its gymnasium is testing two appeals. Of 100 residents approached with appeal A, 21% pledged a donation. Of 150 presented with appeal B, 28% pledged a donation. At first, we might be able to see that pledge B with 28% is greater than pledge A, which is 21%. But the first thing that we need to look into is the fact that pledge A is 100, but pledge B is from 150. Further, we're not really quite sure if the difference between these two is merely due to chance or it's really different. Hence, we do hypothesis test on these two population parameters. Now, if we are to compare two population parameters, most probably we will either compare means or we're comparing proportions. Now, if we're going to compare means first, we have to determine whether the two means that we're going to compare are from independent samples or from dependent samples. If we say that our samples are independent, this is literally two different samples. For example, you have male and female, department A and department B, school A and school B, group A and group B in general. However, if you have dependent or paired samples, this is actually just one sample but two data sets. For example, for group A, you got it from weekdays and then weekends. From group A, you got it before the experiment happened and then after the experiment happened. Or you got it in daytime and then nighttime. So that will be important because that is one of those determining factors on whether your on how you're going to compute or what test you're going to use rather. Now, say for example, we would like to test whether these are independent samples or not. Although there are occasions useful to compare the variances of two samples, we also compare the variance of two samples if they're equal for us to determine whether we can use this test, which we're going to discuss further later, to compare our two samples. And to determine whether sigma 1, variance 1 is equal to variance 2, we are going to use what we call the F-test. So the F-test is the sampling distribution of S sub 1 squared over S squared sub 1 over S squared sub 2 rather. And that would result in two samples were repeatedly drawn from the same normally distributed population. The exact shape of an F-test would usually be determined by two different degrees of freedom instead of just one single value. But we're not going to use manual computation now. We're going now to use a different approach. Not a different approach. We're going to use computer applications for us to compute our values for us. Alright. So as we can see here, we are going to use Microsoft Excel for us to have our data computed. Now the first thing to do first is read our problem. A researcher hypothesizes that the average number of sports that colleges offer for males is greater than the average number of sports that colleges offer for females. A sample of the number of sports offered by colleges is shown here. At alpha equals 0.10, is there enough evidence to support the claim? So, since we're going to compare two independent samples, the first thing to do is to determine whether their variances are equal. So, To do that, the first thing to do is to check whether you have this button on your data ribbon. So if your data ribbon has already this, then we don't have much of a problem. But if you do not have yet, this is how you get this button here. First, we go to File. You check, yeah, this one here, File. Then you go down to Options. So once you selected Options, you now go to Add-ins. And in the add-ins, you see this Analysis Toolpath. This is what we're going to do. So click Go. Here, you're going to see these add-ins and make sure that they have check buttons, Analysis Toolpath and Analysis Toolpath EDA. Solver add-on will be useful also for your higher industrial engineering applications. This one here is downloaded externally, which we're going to use in our next lesson. So what you're going to see probably on your own Excel would be this only, including this. But going to use is this, but you're going to use this also in the future. So just check all of that and click OK. Then you're going to see that button already there. So with that, once you click that, you get to see a lot, and this is what we're going to use, F-test. Just to let you know, if you want to also to compute like descriptive statistics, you can use this one, and it will give you mean, median, mode, and a lot of other descriptive statistics. But what we need to use is the F-test. But before we need to do that, there's one requirement in F-test. If you remember, the F statistic is given by S squared sub 1 over S squared sub 2. It is required that S squared sub 1 is the bigger variance out of the two groups. With that in mind, we need to check whether which variance is actually bigger. So for us to avoid doing the test again, remember that Excel is a spreadsheet. So we can use its formulas to compute easily for us. So the formula, to determine whether the variance of the male or the variance of the female is bigger, we can use its formula var.s because that's for sample. var.p is for population. So let's have that equals var.s, and then we select this one only. We don't include the label in Excel formulas. Close parenthesis, then enter. For females, we do the same, var.s. We select this one here. Close parenthesis, then enter. Oops. So as we can see, it's although they're quite close, what is bigger is 10.6698. So this should be our S squared sub 1 and this should be our S squared sub 2, making female our variable 1 and male our variable 2, which we're going to see later. Now that we've determined which is variable 1 and variable 2 now, we can now proceed to our data analysis. With that, F-test, this is what we're going to do. F-test to sample for variances. Okay. So, probably what you're going to see before is blank. So what we're going to do first here, variable 1, what we selected is female, so we select this one here. We also include already the label, I'll show you later why. For variable 2, we select this one here. There we go. So that we include the male and female labels in the table that we produce later on. You check this labels. Alpha, according to the problem, is 0.10. And since at first, when you open it the first time, this is where it would be. But since this says new worksheet, it will just open a new worksheet. Since I want the results in this same sheet, I'll just click output range, then choose somewhere, probably there. So from there, we click OK, and in less than a second, we already have our results. Now, although we can still use the critical value approach, what we're going to do here is the p-value approach. In the p-value approach, we don't actually memorize 3 decision rules, just one. If the p-value is less than alpha, we reject HO. Now, if you're wondering why we did not have HO and HA for F-test, because that's not what the problem is asking. The F-test is just a preliminary test to determine which actual hypothesis test to use. So, for the F-test, if p-value is less than alpha, let's have that. If p-value is less than alpha, that would simply mean that the variance of the first sample of variance of variable 1 is not equal to the variance of variable 2. So with that in mind, we have this table here. We can see that it computed the mean of the two samples, the variance of the two samples, then the sample sizes, and then the degrees of freedom. This is the test value or the F value. This is the critical value, and this is the p-value. It's right there. So now, based from this, let's make our decision. The p-value of 0.49334 is what to compare the alpha of 0.10. As we can see, the p-value is greater. So we have failed to reject our HO. The HO for variance. Failed to reject. Failed to reject our HO for variance. Therefore, we say that the variance of these two samples are equal. And that would be an important factor in deciding which test to use. And that is the F-test of two sample for variances. So, let's have another example of that here. Let me clear those up here. And we have this one here. There we go. So, we have a researcher wishes to see if the average length of the major rivers in the United States is the same as the average length of the major rivers in Europe. The data of the sample rivers are shown here. At alpha equals 0.01, is there enough evidence to reject the claim? So, pause the video and try to see if you can determine whether they have equal variances or not. Alright, so the first thing to do is to determine which variance is actually bigger. Is it the variance of the US or the variance of Europe? So, we compute the variance for the US dataset. There you go. While the variance for the Europe dataset, so as we can see, the variance of the Europe dataset is bigger. Hence, we know that this would be, change the color. This would be our variable 1, and this would be our variable 2. So now let's proceed with our F-test. We go to data analysis, F-test again. So this time we have our, just from here we select, go. That's our variable 1, the one from Europe, and then variable 2 will be the one from US. There you go. Now alpha is different here, it's 0.01, so we have to take note of that. We still included the labels. And I want just the output a little closer. So there you go. So as you can see here, we now have different degrees of freedom because if you might have noticed, we have different sample sizes. So we have our p-value here, and as we can see, if we compare the p-value of 0.37974 compared to the alpha of 0.01, this is bigger. Hence, the variances of these two datasets are also equal. And that is the F-test for two sample variances.